Okay, welcome everyone. It's a pleasure to introduce today's speaker, Daniel Bump. He's a professor for mathematics at Stanford, and he works on representation theory in automorphic forms. And if you don't know what it is, I don't know either, it's hard to explain, but it has some general relationship to this kind of toy, which I think most of you are familiar with, and he also uses this actually in his own teaching to explain to students these kind of concepts. And I think this also shows a general thing that many mathematicians actually love games and toys, and playing games actually has also informed lots of interesting mathematics. And one of the other games that Daniel loves is the game of Go. It's an ancient game. It's one of the oldest games we know, and that it's still played. And Daniel was actually a co-author on GNU Go, which was one of the first free Go programs of reasonable strength in the 1990s. And you may have heard the news of the last couple of weeks where Computer Go has made a tremendous advancement. So there was this program AlphaGo, which beat one of the world best players. And this is not only a significant advancement for the game of Go and Computer Go, but also artificial intelligence in general. And so it's very timely to have him here today to speak about talk, a very simple titled Computer Go. So welcome.
So this talk is going to be sort of a mixture of discussion of the history of Computer Go and some technical issues, and I hope to end looking a little bit at the developments of the last 10 and 5 years, and in particularly the AlphaGo match. So the very first computer program that anybody is aware of was written in 1968 by Zobrist, who was a doctoral student at the University of Wisconsin. And his program was somewhat ahead of his time because it used concepts that have proved important. One is Zobrist hashing, which we'll probably touch on, and then there's the influence function, which we'll definitely touch on. Beyond this, things started to happen in the 1980s. Usenix was a Unix users group, and around 1984, they started having Go tournaments. The second one is in Portland, and I happened to be there. Although I wasn't involved in computer programming at the time, I happened to be in the room when this tournament was held, and it was organized by Peter Langston, who was a musician, and also a programmer, and they played the tournament on Sun workstations, as I recall, and there were glitches. Nemesis crashed, and although Nemesis was the strongest program and was favored to win, it didn't win. Instead, one of Peter Langston's two programs won. It was at Portland State University. It was quite interesting, but everything was very primitive. So in the 1990s, things started to take off, and I'll mention some particular programs. HandTalk was the strongest program, at least for a while. Many Faces of Go was written by David Fotland, who I believe was an engineer at Hewlett-Packard, and eventually retired to work full-time on his Go program. Other well-known programs were Goliath, Smart Go, Nemesis, which I've already mentioned, Go4++, and a strong program from North Korea. All of these programs were they were strong enough to give an amateur, a weak amateur, a challenge, but not a player of even middle amateur strength. So the ratings of them were something like 9Q or something like that, if you know what that means, quite weak. But still strong enough to be interesting, and that programming issues came up. Computers, well, laptop computers didn't really exist yet, but you did have PCs, and you could connect two PCs together with a cable and start a program on one PC and another program on another PC, and if everything worked, then the two programs could play, and there was a protocol for exchanging the moves. Every byte, every individual byte contained a move, and so they were not readable, human readable, but if everything went well, then the two computers could play, and this is how tournaments were conducted. Around 1992, the Go culture started to change because of the rise of Go servers. So there were chess servers that were starting to come up, and the Go servers, the Internet Go server was started by Tim Casey, who was here in Mountain View, and Mark Okada in San Francisco. They moved their server around from New Mexico to Pennsylvania to San Francisco, and eventually they sold it to PandaNet in Japan, and now it is PandaNet. There was another server called the NNGS server, which copied the IGS protocol, so that the clients that were written by third-party people for IGS could use the NNGS server, and the IGS people were quite bitter about this and quite angry about it, and so there were a lot of very hostile email messages and so forth going back and forth. Eventually, NNGS went out of business, but for a while they were where most of the programs between Go, the matches between Go programs took place. Now things have moved to KGS, which is a server based in Portland, Oregon. So the first programs had to have their own, they were commercial programs, and they had to have their own built-in graphical user interface so that people could stand to play with them. And you basically loaded the software onto your computer and then played with it. But with the servers, clients began to be developed, and those were capable of interacting independently with the server or with the program or with the human. And so things changed, and they got a lot nicer when this happened. The Go modem protocol that I mentioned went out the door when a reasonable ASCII protocol was developed by Gunnar Farnabeck with GNU Go. We had to get permission from Richard Stallman to use a different licensing for the particular files in the GNU Go distribution, so that they could be used in a proprietary program. Most of the files are licensed GPL, but the ones that operate the protocol are licensed BSD or X11, which means that they could be taken and put into a proprietary program. So there's a quick classification. So we could classify Go programs as commercial or research or free. I guess the first two categories are not mutually exclusive, and the last two categories are not mutually exclusive. But a commercial program is one that you can buy from somebody, and these are always closed source. The free programs include GNU Go and also some stronger ones. Particular Pachi is the strongest free Go program, and I'll come to these programs later. So a research program would be something like AlphaGo, which might or might not have source code available to them. So I'm going to talk about GNU Go for a little bit. So there was an article in Byte magazine about a program called Wally by somebody named Jonathan Mullen, and Manlung Lee, who worked for Microsoft, took that and wrote a free Go program and got it part of GNU, which means it was distributed under under the GPL as part of GNU. Because it was open source, you could take it and you could start modifying it. And I noticed that it was capable of some obvious improvements, which would make it stronger. And what I didn't realize was that once you start doing that, you get sucked in, and it's like it takes over your life for a while. But so anyway, I wrote a program called Liberty 1.0, and that program is still available on the internet. If you go to the KGS server, somebody in Finland is running a Liberty bot. I don't know the person that's doing that. So anyway, 3 things happened. I was contacted by Jan van der Steen in Holland, who had his own program called Liberty, and he objected to the use of the name. I was contacted by Stuart Craycraft and Richard Stallman with the Free Software Foundation and asked if we could take Liberty and make it into GNU Go. I was concerned that Man Long Lee might not be happy about it, but he was okay with it, so we started working on it. I was contacted by another programmer named David Denholm. He worked for Citrix UK, and so we started working on it. We were unable to release our code because the Free Software Foundation required a copyright assignment, and they required it from not only David but also from his employer, Citrix. And Citrix was very slow about doing this. So the result was that we worked together without anybody else seeing our code for several months. And finally, in April, we got the Citrix software copyright assignment, and so we were able to release GNU Go. And immediately, other people wanted to work on it. I'll mention Gunnar Farnabeck because he was probably the strongest programmer. He's somebody that works in computer vision, and he's very good. He had a lot of vision about how the program should be developed, and we made it into quite a respectable program, though still not at the level that a middle level amateur program player would be challenged by it. It's a good program for beginners, and we had a lot of help from a lot of people. I've mentioned a few of them. The development slowed after 2004. Gunnar got a job and he had a child, and even more than that, we started realizing that GNU Go could not compete with the Monte Carlo programs, which I'll discuss later. So the last stable release was 3.8 in 2009. And there's still a Git repository. Somebody could start enhancing it, but it would probably be better to start from scratch using a different paradigm. So now I'm going to show you some of the issues that face anybody that's programming. So by reading, I mean search. In computer chess, it would be called search, but reading means that you envision future positions in your mind, and you try to figure out what you can do. In chess programming, it was found that brute force search, that you search an enormous move tree, evaluation of the terminal nodes in the tree is very easy, and so you can search an enormous tree and you can basically find the best move by means of that. That was sufficient to beat Garry Kasparov. That doesn't work in Go. And the reason is that in Go, evaluation of the terminal nodes of the tree is already a difficult task. So at the terminal nodes of the tree, you will find that some of the groups on the board are alive, some of them are dead, and some of them are critical. If there's a critical group on the board, that means that life or death of that group depends upon who plays next. It may even be that there are adjacent dragons, one of each color, which are both critical, and one of them is going to die and one of them is going to survive, and this is called semi-I. So the decision as to whether a group is alive or dead or critical itself requires quite a bit of analysis. This means that the evaluation of the terminal nodes in the tree is not trivial. So I'm going to show you an example. So I asked GNU Go to evaluate the position in the upper left-hand corner. So this is a critical position. If white moves first, he can kill. If black moves first, then it's possible to live. The variations form a tree, which is displayed down in the right-hand corner. So the very first move, if you want to kill, is this one. And once this stone is placed, there's no way to live. Black can try this way, but there's a refutation. And this group does not have two eyes, which, if you know the rules of the game, mean that it's dead. And even if you don't know the rules of the game, it means that it's dead. So there's no way for this group to live, and this sequence of moves shows that. There's a variation. Instead of going here, black could try to go here, but that doesn't work either. On the other hand, if black plays first, this move forms two eyes. It carves out two separate eye spaces in the corner, and consequently, there's no way that this group can be killed. So GNU Go can figure this out, not too inefficiently. But how does it do it? Well, it has to find the right move. So for example, here, it has to find this move. And the comments here tell you what GNU Go did. So I wonder, is that very readable? Oh, okay. Well, I'll tell you what it says. So first it says A1303. Okay, so now if you look in the GNU Go source code, there are many patterns which are encoded graphically like this. These were written by hand, then they're compiled to C. The X's mean, in this case, black stones, and the O's mean white stones. The question marks means that the color of the stone is irrelevant. The star is the move which is proposed by this pattern, and if this pattern is found, then that move will be tried, and that's what happened. So the problem with this is that all of these patterns were hand-coded by people that were analyzing GNU Go's games, finding its mistakes, saying, well, this it would play correctly if we change this pattern here. There's a test suite in which we run a bunch of tests, things that have been fixed in the past. If something else we do breaks them, then tests are going to start failing, and we'll find out that there's something wrong with the pattern that we've added. And this is time-consuming, and it is also of limited success. This is perhaps not the way it should be done. It works up to a point. Okay, so this is what I have to say about reading. The other thing I want to talk about is influence. I'm going to use one of the AlphaGo games in order to illustrate this concept. So the ability of a group to live inside some region depends a lot upon the surroundings. If the opponent has a lot of walls in the vicinity of that stone, then it may be difficult to live. And so we have sort of an intuition that, let's take this. This is the third AlphaGo-Lee Sedol game. And I want to look at the bottom here. This region in the bottom is AlphaGo is white. White's influence in the bottom is very strong because it's completely surrounded by walls. Black could try to go in, and perhaps black could make life, but it's very unlikely. Nevertheless, Lee Sedol invaded there, and this is because he knew that he was behind. He started to go in, and the fact that white's influence is so strong means that this is a very bold and courageous thing to do. So he makes a forcing move, and AlphaGo doesn't even answer it. It plays up here. The influence is so strong that it doesn't look like there's any way that black can make life. Nevertheless, black was able to make what's called a ko, which is a kind of a situation where the life and death depends upon the outcome of a fight that may globally involve other parts of the board. So this was quite a success for Lee Sedol, was to make this ko. Unfortunately, it wasn't good enough because he was not able to win the ko. When I say that a ko depends upon other things that happen in other parts of the board, the rule of ko, this stone has just been captured here. The rule of ko says that black may not immediately recapture it. If he doesn't recapture it, white can fill there and win the situation. But since he cannot immediately capture it, the rule of ko says he has to do something else. So he goes over here. He makes a ko threat. A ko threat is a move in perhaps another part of the board, which has to be answered because the gain that he would get from killing something over there would be adequate compensation for losing the ko. So AlphaGo answers it, and so the ko fight continues. Unfortunately, AlphaGo had a local ko threat local to this situation, and Lee Sedol realized that he did not have enough ko threats outside, so he resigned. I've digressed a little bit to show you part of the game, but I want to make the point that influence, meaning sort of the sense that these white stones, if I do this, you can see, these white stones sort of radiate a power that fills up this space. That's our intuition, but somehow capturing that idea is an important issue in Go programming. So we need to have an influence function. So I'll go back to the. So the influence function first appeared in the very first program in 1968. This program of Albert Zobrist, and this is maybe I can show you. Here I'm running GNU Go, and I'm asking it to do a bunch of analysis and show me the results. So it generates a whole bunch of different diagrams, of which this one shows the status of the groups, what it believes is live and dead. It believes this group up in the upper corner is critical, but in fact, Lee Sedol is alive up there. GNU Go has that evaluated wrong. This shows the influence, and you can see at the bottom here that so the influence is actually a number. The green is very strong influence, but then other colors, red means a low amount of influence. Yellow means a medium amount of influence. The influence function is intended to capture the intuition that these white stones are radiating some quality which controls whether it's possible for black to live or die inside. Up until around 2006, all Go programs, we believe, worked more or less the same way. Of course, we haven't seen the source code to the commercial programs, but we have some idea how they work. Really, I kind of showed you that there's hand-coded patterns which determine the reading, and there's an influence function, and all of these programs probably are very similar in architecture. But then the Monte Carlo programs came on the scene. They still require a database, but they have much better success. And then very recently, the Monte Carlo methods have been supplemented by deep learning. Before I come back to these things, I'd like to mention a couple of things. Combinatorial game theory is sort of a digression because the ideas of combinatorial game theory haven't been very much applied within Go. Nevertheless, they're very good at analyzing endgames. Combinatorial game theory is a branch of mathematics. It was found, the first papers that I'm aware of, there was a paper by John Milner in 1953, and then John Horton Conway came on the scene, and he developed it into really a branch of mathematics. And so these books are quite excellent and well worth your time if you happen to pick one up. I will mention that one of the hotbeds of Go development was the University of Alberta in Edmonton. Martin Muller was a postdoc in Berkeley working with Elwyn Berlenkamp. He's a 6-dan Go player. And then anyway, he went to Edmonton and he founded a research group. And a lot of good stuff has come out of there. In particular, the AlphaGo developers came out of Edmonton. They went to England and developed AlphaGo, but they got their start in Edmonton, and many other developments came out of there. So now I'm going to talk about Monte Carlo methods. So the idea of Monte Carlo search would be that instead of searching a limited move tree, spending a lot of time evaluating the terminal nodes, maybe you just read all the way out to the end of the game. At that point, there's no issue of life or death. So you don't have to you don't have to waste time deciding whether a group is alive or dead, which, if you make a mistake, will invalidate your evaluation of the terminal node in the move tree. You just read it out to the end, and then everything is obvious. The dead stones can even be removed from the board. So you sort of play not completely randomly, but you use a pattern matcher that is tuned for speed, and then you make many trials, and from the data that you collect, maybe you can figure out the best move. So the origin of the algorithm which is used now is called UCT1, and it addresses the following problem. Suppose that you have a large number of slot machines, and and they might not all be equal. Maybe some of them pay better than others. You want to figure out which ones you should be playing. So you want to play the one that seems to be winning, but you don't want to neglect the other ones, because if you do, you might be missing one. Maybe you have a bad luck with one machine for a while, but it's actually better. So there's a deterministic strategy for doing this, which is called UCT1. You maximize the following function. So the first one, for J is the number of the machine, and I see I can't move the cursor left hand. The first term is the average rate of payoff of this machine. And so clearly you should play the machine that gives you the best payoff. But the second factor decreases as you play a lot of, if you play that machine a lot, it decreases slowly enough that you're also playing the other machines. So this is called UCT1. And it can also be applied to tree search. Now this was first done by these Hungarian guys whose names I would probably mispronounce. They were not interested in Go programming as far as I know, but they adapted the UCT algorithm to tree search. And then Sylvain Joly was, in his dissertation, applied this to Go, and this became a Renaissance thing. Oh, I see there's a sentence that's missing here. His dissertation also used reinforcement learning, which is a key principle in training neural nets. And then he went on to author a Go program called MoGo, and MoGo had some success. So in 2008, MoGo played a game with Myung-Hwan Kim, who is a 9-dan professional. If you watched the videos of the AlphaGo match, there were two sets. One was commentated by Michael Redmond and Chris Garlick, but the one to watch was commentated by Myung-Hwan Kim. So he's a professional Go player. He's a 9-dan, which means he has the highest rank that you can get, but he's still not quite at the top. He's not as strong as Lee Sedol, for example. He lives in Los Angeles and he teaches, and he lost by 1.5 points. He lost a 9-stone game to MoGo. 9-stone is a big handicap, so you can see from that statement how far we've come since 2008. And then just 3 years ago, a couple of Monte Carlo programs, Zen, which is authored in Japan, and Crazy Stone, which is authored in France, defeated a couple of the former world champions, Masaki Takamiya and Yoshio Ishida. Both were at the top of the Go scene, in the 1970s, and so although they're like my age or something, they're still considered top players. And at that point, it seemed, and in fact, just until a year ago, it seemed that the top programs were 4 stones weaker than the top professionals. A 4-stone handicap is a big handicap, but it's not so big that this wasn't impressive. It was very impressive. But nobody was prepared for the recent developments. Neural nets have had amazing success in the last 5 years in all sorts of things, such as image recognition and medical diagnostics and the key to this have been faster processors, particularly the use of GPUs, which were designed originally to display computer graphics, but were repurposed for training and evaluating neural nets. So there's I can give you another demonstration. So this is a neural net which actually is written in JavaScript, and it actually plays in the browser. So this is by some guys in Edmonton. Edinburgh, in Scotland. So this neural net has very good intuition. It plays quite well, and if you play with it, you'll be surprised at how well it plays, given the fact that it's not doing any reading. In order to defeat it, you should start a fight and make some trouble, and then it starts making mistakes. But in terms of playing the opening and developing influence and everything, it plays just amazingly well. It's written in JavaScript. You can go to GitHub and get the source code if you want to see it. So neural nets give a much better way of pattern recognition than you saw with GNU Go. What did we do with GNU Go? We had handwritten programs, handwritten patterns that were written by humans. If a pattern is missing, then you have to code it by hand. In this case, what they did, and in the case of AlphaGo, what they did is that they trained the neural net by playing a lot of replaying a lot of professional games that that had been archived. And in the case of AlphaGo, they did something else, which is they allowed the machine to play itself, and they used reinforcement learning in order to tune the neural net. So neural nets are quite amazing. They're also kind of scary. I mentioned some of the intangible things that are part of the art of playing Go. Vital points and tsujis are key points in a position. So you want to occupy the vital point. The relevant intuition is called shape, that you try to have good shape. But not only that, but timing is very important because you need to play the moves in exactly the right sequence. In certain situations, if you play things in the wrong order, then there will be a refutation. So it's very delicate. The neural nets are, and also I mentioned thickness and decision to sacrifice stones in order to gain thickness. These are all intangible things, but the neural nets are often able to find the right move. For example, the neural net that I just showed you, and obviously the ones that are used by AlphaGo. I should mention Facebook also has a program which, as far as I know, has a similar architecture to AlphaGo and is, perhaps a little bit behind AlphaGo. It plays on the KGS server. It was quite remarkable to see how fast it improved. And I think if AlphaGo hadn't come on the scene, then maybe Dark Forest would have taken its place. So the AlphaGo architecture is discussed in a Nature article. They have two neural networks. They have a slow policy network. This is good at choosing the moves. The rollout policy is not so good at finding the right moves, but it's very fast. And so for the Monte Carlo method, you want to play the game out into the, perhaps to the end. And so you need two different styles of play there. And so they have two neural nets. These were trained by self-play. And if you want more information, there you can find the Nature article. So I guess I had we have a few minutes. So I could look at some of the AlphaGo games. And I also have Lee Sedol is arguably the strongest player. There's a young Chinese guy who thinks he's stronger because he defeated Lee Sedol more in tournament play. But Lee Sedol has been at the top for 10 years, and he's right in his prime. And these games were played very well by Lee Sedol. He didn't make mistakes. Rather, what happened was that things happened that would not be considered a mistake by human standards. He wasn't prepared for AlphaGo because AlphaGo played some games in October against Fan Hui, who was maybe the strongest player in Europe. He's a professional Dahl. And AlphaGo won all those games, but they were not impressive because AlphaGo played very cautiously. This is typical of the Monte Carlo programs, is that it's very easy to underestimate them because they know if they're ahead. And you may not, a position may seem evil even to a human observer or player, but the Monte Carlo program has a better sense than you do of whether it's ahead or not. So it may play very cautiously, and the play may therefore not be impressive. So Lee Sedol didn't know how strong AlphaGo was, and he played an unusual move right at the beginning. This move is not a standard opening move. Probably his reasoning was that he thought that maybe AlphaGo had a book, and the problem is to get out of the book. So you play a move that's a little bit non-standard, and AlphaGo cooperated by letting black build up his side. So now black has to play lightly on the top and settle things, but Lee Sedol is good at that. This move is probably an overplay, and he might not have played it if he had realized at this point how strong AlphaGo was. So AlphaGo did this, and this move is also black's chance to back off, but he didn't back off. And now these black stones are cut off. That's okay. Lee Sedol is perfectly capable of making life. Now white has been cut into 3 parts. And although black stones here are kind of in trouble, these stones are now perhaps settled, but these stones are potentially in trouble, and black can use that in order to make life. So after black goes this, white has to go back and defend, and black goes here. And at this point, to somebody like me, it might look as if black has some danger, that the black stones still could die. But in fact, there's just enough potential in the situation that black can live. But white has gained some power on the left-hand side. And after this, neither player really made any mistakes. And when the smoke cleared at the end of the game, black, Lee Sedol, has made some territory down here, but white is getting territory on the top. And here, AlphaGo played some moves that people would not think of. So this is a very surprising and unusual move, but it's okay. And AlphaGo knows exactly how much it needs in order to win, which it does. It has to invade on the right-hand side. But this invasion is kind of non-obvious, and I believe that Lee Sedol was taken by surprise. There was a lot of, so white, AlphaGo, has succeeded in catching some stones up here, and also living in this corner down here, and also taking a large territory here. And although it's given up some territory here, it knows exactly that it's ahead. And after a little while, Lee Sedol gave up. People tended, after a while, people tended to anthropomorphize AlphaGo. Maybe I'll show you a video of Myung-Hwan Kim. I mentioned him. He was the one that played Mogo. He always referred to AlphaGo in the female. So she did this or she did that, and his commentaries are very good. The 4th game was the one that Lee Sedol won by playing a brilliant move. Let's see. In game 4, AlphaGo slowly got an advantage. Lee Sedol is white. he more or less made some forcing moves, and the rule in Go is that forcing moves can be thought of as being light, that you can give them up. If you make forcing moves, you give them up, and so he's not committed to saving these white stones here. They were played as forcing moves, but nevertheless, AlphaGo seems to have captured them, and although white, Lee Sedol has gone in compensation there, it looks as if he's behind at this point. Lee Sedol played a brilliant sequence. At this point, he thought for about half an hour before he played this move, and he didn't have that much time on his clock. So by the time the sequence was over, he was very short on time. And then he played this move. This move is a move that I would not think of, most players would not think of, yet it is the only move that works in this situation. AlphaGo could have played better. There was another way in which Black could have partially recovered this, but if that had happened, it would have been a very close game. The reason that this works depends upon complicated sequences. After this, AlphaGo started making mistakes, which is something that happens with Monte Carlo programs. That if they are behind, they may make some errors. There is a remedy for that called an internal commi. So if I have 5 minutes, maybe I'll play you 5 minutes of this YouTube video. Is that okay? Okay. So this is Myung-Hwan Kim and Ha-Jin Lee. Ha-Jin Lee is a very popular blogger. She's a professional Go player, and she has a YouTube channel which is extremely popular. So she's the lady, and this is Myung-Hwan Kim. He's the pro that lives in Los Angeles, and they're struggling to figure out some variation, and they're trying all different things. Lee Sedol has not yet played, so Lee Sedol is up in the upper left-hand corner.
Let's talk after you count.
Okay. So 66 is what Black has in the other side?
Yes.
And white, it's very difficult to count the left side. So let's say
Without white.
the right side.
Right.
Almost 50. That's really good. Maybe it's less than 50.
They're sort of in despair because they want Lee Sedol to find something, but it doesn't look like he can. He's counting, he's evaluating score.
Black has less than 10 points winning on the board without counting anything on the bottom side and the center. So Black should make like 15 points.
Right.
15 points, so seems like it's not very difficult to make.
Right.
Might be even sentence.
Right. I think so. Why do we need to save the 3 stones in the center?
Yeah, right. No, because Black here just center, and that's definitely.
I believe I backed up too much, so I'm going to move it ahead a couple minutes.
And then John.
That's very good.
At this point, Lee Sedol has started to play, but he hasn't played the vital move.
I was just wondering why should cut actually.
So you can see that the stone,
Yes. That one.
the stone, it was there and now it's disappeared, but it was on the board. So the commentators had actually found this move, the move that Lee Sedol played. Ha-Jin Lee found it in the middle of a long sequence, and then Myung-Hwan Kim found it at the right place, but he couldn't decide whether it worked or not. And they were analyzing until finally Lee Sedol played the move, and then they continued to analyze. It's a very dramatic video, and perhaps I should stop. But if you're interested in this, it's high drama on the Go board, and everybody, even if they're kind of interested in seeing progress in computer Go, was rooting for Lee Sedol. That from the human angle, he just showed so much character in the way he conducted the match, and it was good that he got a win. At the same time, there was a tendency to perhaps anthropomorphize AlphaGo a little bit. AlphaGo was awarded a trophy or an honorary 9-dan certification by the Korean Go Association, who praised AlphaGo's sincere efforts to improve at the game, and because it involves neural nets, there's something which is perhaps not a mind there, but it's getting there. That there's elements of true thought in AlphaGo, unlike the computer chess programs that happened in the 1990s. So I'll stop there.